it!
No. Okay, so 4-6. 4-6. We're going to talk, it just talks about isosceles, equilateral, and right triangles. Just some other kind of odds and ends, random stuff that we're going to add to what we already know about these guys. Quick review of isosceles triangles. Remember, we said earlier in the year that isosceles triangles are triangles that have at least two congruent sides.
Yes.
So are equilateral triangles isosceles?
Yes.
Yes, they are. They are. Because they have at least two congruent sides. They have three. They're just special isosceles triangles. Okay, so we said that for an isosceles triangle, the two sides that are congruent are the legs. And then the third side we call the base. Now we're going to add something else that we didn't have before. The angles that are opposite the legs are called the base angles. Easy to remember because they're the angles that sit on the base. They're attached to the base, right? Okay, and then here's the vertex angle at the top. So what do we know? Now, the base angles theorem tells us that if two sides of a triangle are congruent, in other words, if it's an isosceles triangle, then the base angles are always congruent. So the angles opposite the legs are always congruent. So we can do this. Whoops. We always know that. Okay? Base angles of an isosceles triangle, always congruent. We also know the converse of that statement. So we know that if we have a triangle with two congruent angles, then we also know it's isosceles. And so the sides opposite those angles are the legs. And they're congruent. So it works both ways. Okay? So that's the base angles converse. The other one was the base angles theorem. Okay. Before I forget, you two, stop. Drew, why don't you scoot back a little bit? Just let's say the thing. Okay. Before I forget, on the 4.5 assignment, I tried to do something really nice for you, and it sort of backfired a little bit. I tried to set it up so you could use the pull-down menus for the reasons on 4.5. Yeah. So you notice that it looks really strange. Okay, what I had to do, if you had finished it completely and had 100%, I just left it in there. Even though it's going to look funny, the score will still go in the grade book. If you had done part of it but hadn't finished it, the way to fix it, unfortunately, was I had to delete all those attempts. And so when you go in and start a new attempt, it'll look great. You'll have fancy pull-down menus, but unfortunately lost all the stuff. There's only 5 for all. It's not that big a deal. So sorry. That's the. I tried to be nice, but it turns out that I actually was pretty mean by accident.
Oh,
so.
Meanie.
Yeah. Okay, so I want to show you a quick proof. Now, I'm not going to write this out, but let's just see if we can talk through this. There's a new kind of a strategy or technique we're going to use here that we haven't done before. And we're not going to spend a ton of time on these proofs, but I want you to see this. Let's say that we want to prove the base angles theorem. So we're given that triangle, triangle ABC, right? And we're given that side AB is congruent to side AC, which we've got marked on here with the red congruence marks. Okay, we want to prove that the base angles are congruent. We want to prove that angle B and angle C are congruent. Now here's the trick that we haven't done before. We're going to draw in a part of this picture that wasn't there to begin with, and we can do that in a proof. We're going to add segment AD. So we're going to add point D, and we're going to create this segment AD such that we're going to draw it, and we're going to say we want angles BAD and angle CAD, these little angles right here, to be congruent. Okay? Now we can do that. We can specify that. So we're going to create this stuff, we're going to draw that in, and we're going to use it in our proof. Now why do you suppose that's useful? What have we done there? What do you think?
No, it adds another reason to why BSC works.
Okay. Now look, what we've done here, by creating segment AD, I've partitioned this big triangle into 2 smaller triangles, right? If I could show that those 2 smaller triangles were congruent, I could use that trick that we talked about last Friday, I think it was. No, hold it, last Thursday for you guys. The CP-CTC trick, right, from 4 or 5. Remember that one? If we can show that 2 triangles are congruent, like in this case, if we could show that triangle, let's see, what is this? This BAD triangle CAD, then we know that angle, angle C and angle B correspond, right? Does that make sense? They go together, those angles go together. So by CPCTC, corresponding parts of congruent triangles are congruent. CPCTC. Angle B would have to be congruent to angle C, right? Does that make sense why we'd want to do that? All we have to do is just show that those two little triangles are congruent. Now, how many congruence marks do we need to do that?
3.
3. We got 2, right? We've got the original 2 that we started with. We've got these 2 that we created because we said we're gonna draw this segment so that those angles are congruent. We just need one more. Where's it gonna come from?
Line 80.
Yeah, line AB, the shared side, is congruent to itself. And what's my reason for that?
Reflexive property.
Okay, by reflexive property. And so then, now we can see that the top triangle and the bottom triangle are congruent. And so by CPCTC, we got our proof. Okay? So the reason I just wanted to show that to you is that it's different. We actually drew some stuff into the drawing that wasn't given to us. It wasn't there originally, but that's okay to do. Just want you to be aware of that. Okay, so what else? We know, okay, something else. Okay, we know that an equilateral triangle is a special kind of isosceles triangle. Obviously, we know all sides are equal. Equilateral means equal sides. All sides are congruent. Here's something else we know. We've got these 2 corollaries that we can take together. And what they tell us is that equilateral triangle, a triangle is equilateral if and only if it's equiangular. So in other words, whenever you see that if and only if, it's like a 2-way arrow. It works both ways. If a triangle is equilateral, then we know it's equiangular. If it's equiangular, then we know it's equilateral. They always go together, okay? And you were aware of that probably, but there it is, black and white. Okay, now here's the other one. Here's one of the 2 problems that I kind of want to focus on. You see a lot of problems like this on the review, and I think this is in the 4-6 assignment. There are a couple like this too made. I know there are a lot of them on the review. Where we've got to solve for the variables given that picture. Okay? Now these are like a puzzle. These are kind of like those ones we did back a chapter or 2 ago. Remember we had to just, I think it was last chapter, we had to fill in all those little angles to try to find, they gave you something about an angle clear up here and asked you about one clear down here and get to fill in the whole thing. Kind of like that. We've got to sort of fill in the blanks here as we go, and in the process of doing that, hopefully, we will discover what these variables are. Okay, so any ideas how we could solve for one of those to get started? Oh, okay, yeah, now look at this, look at the left triangle, the blue triangle, right? It's equilateral, and so therefore it's also equiangular, right? So we know that all of these angles are congruent. So if that's x, and that's x. And what do they all add up to? 180. So we got an equation. X plus x plus x. So 3x equals 180. So what's x?
60.
60. Right? We got it. X is 60. Okay, so then we can, let's go down here and we can just write that in, can't we? We'll write in those 60s, so that's 60 degrees, 60 degrees, 60 degrees.
Just like linear pairs.
Okay, good. And then we got a linear pair. Here, no. Linear pair adds up to 180. So what's this guy? If this and this have to add to 180, what's this guy? 120. Okay, so 120 degrees. Now what?
Y is the same.
Oh, okay, it's isosceles, so I know that by the base angle theorem, I know that those 2 angles have to be congruent, so that's also a y. So now what's the other equation I come up with for y? Okay, good. Y plus y, so 2y plus 120 equals, good. So now to solve for y, I just subtract 120, so 2y equals 60, so y equals 30. Very good. Okay? Make sense? Okay, good. All right. Okay, the other thing that they give to us in 4-6 that's kind of useful is This. Okay, we have learned there's 4 ways to prove triangles are congruent. The 4, 4, 6. For any triangle, we know that if we get 3 congruences in the patterns SSS, SAS, ASA, or AAS, I know the triangles are congruent. Now, we get an even better shortcut. If we're dealing with right triangles, we have the hypotenuse leg congruence theorem. What this tells us is that if we have 2 right triangles, if the hypotenuse and 1 leg of one right triangle are congruent to the hypotenuse and 1 leg of a second triangle, then just from those 2 congruences, I know that the triangles are congruent. And really, we're sort of cheating, because if they're right triangles, we actually have a built-in third congruence that we just don't have to write. Because the right angles are all congruent. Make sense? Okay? So there's our HL congruence theorem. You get some practice with that. Really easy to use. Same idea as the other ones, only easier because you only need 2 parts instead of 3. Okay? Now, the last thing I want to show you is I want to do an example. I want to do an example of a problem from the first review assignment. And there have been some troubles with this, and I understand why. It's a little tricky. Okay, so how about... In fact, I want to pull a different one up. Let's try this guy. Okay. So here's the kind of stuff they're asking you to do. They want you to, they tell you, we want to classify triangle ABC by both sides and angles. Now they're giving us the coordinates of the 3 vertices of the triangle, and they're asking you, and this is kind of helpful, they're asking you to fill in the lengths of those 3 sides. Okay, so let's calculate this. We're going to have to use the distance formula. So somebody, now remind me real quick, what's our distance formula? D equals square root of parentheses y2. Okay, good. X, and for this one, we can even do, I mean, that's fine. We can start with the y's, or we can even start with the x's. Doesn't matter. We're just doing x2 minus x1 squared plus y2 minus y1 quantity squared. Okay, thank you. Welcome back. And then we're just going to plug in the numbers and find out what all those distances are, right? So let's find out what AB is. So what's, now for AB, let me write these down again. Here's A. I'll make them a little bigger so you can see them. A has coordinates negative 5, 1. B has coordinates 0, 2. So what am I subtracting from what in the distance formula for AB?
0 plus 5.
Okay, 0 minus negative 5, so 0 plus 5 squared plus 2 minus 1, right? That makes sense? Okay, and so then if I do that on my calculator, let's see what we get. So, let's see.
26.
Okay, I get the square root of 5 squared plus 2 minus 1 is just 1 squared. So 26, that makes sense? 5 squared is 25 plus 1 is 26. So the square root of 26 is about 5.10, the 2 places. Does that make sense? Do you see why? I got to round up this 09, but then the next digit's a 9, so it pushes it up by 1. So it makes that 09 into a 10. Okay, so I get roughly 5.10. Okay, let's do the same thing for BC. Okay, here's C. C has coordinates 3, negative 2, right? So BC would equal the square root of what minus what?
Negative 2 minus Wait, -2 minus 2.
Negative 2 minus 2. We can do the y's first, that's fine. Negative 2 minus 2 squared, right? Plus 3 minus 0 squared. Okay, so that's equal to square root. What's negative 2 minus 2? Negative 4, but do we ever square a negative?
No.
Nope, square the positive. So we get 4 squared plus 3 squared, so that's 16 plus 9 equals the square root of 25. What's that? 5. Okay, so BC is 5. And then how about AC? So AC looks like it's going to be 3 minus negative 5, so that's 8. Agreed? 8 squared plus negative 2 minus 1 is what? Negative 3? So I'll square positive 3. Okay? You with me on this? Am I going too fast?
No.
We good? Okay, so then that's equal to what? 64 plus 9 is 73? Square root of 73?
I want to retake the oath to beaker.
Ah, okay. Give you a chance.
Not really that.
So about 8.54. So we got these three sides then. Okay. So we got the three sides, 5.1, 5, and 8.54. Now if I draw, so what's the biggest side?
The
8.54. And I just write those in here, right? That's what it wants for those answers. 8.54 is the biggest side. Now I want you to make a prediction for me. If we're looking at triangles, if I've got, let's say I've got, these are the lengths of the sides of this triangle. I'm not drawing it to scale, but if that's 3 and that's 4 and that's 5, can you tell me which angle is the biggest angle?
AC.
Mike, what do you mean by the 5? Which angle is it? You mean the one opposite 5?
Yeah.
You're right. Okay, I know, sorry about it, you're getting the wrong spot next to the mark. You're right. The bigger the side, the bigger the angle that looks at that side. Okay, so I know for a fact then that this angle right here is going to be the medium size angle. This is going to be the small angle because that's opposite the 3, and that's going to be the large angle because it's opposite the 5, right? So if I take the numbers from the last problem, weren't our numbers 5, 5.10, and what was the last one? 8.54. So if I wanted to make a triangle out of this, I know that the biggest side is opposite the 8.54. Okay? So it's going to look something like this. Okay. What can you tell me about this triangle so far? AJ, I've asked you already. Right. Next peep, you're gone. What can you tell me about that triangle right now?
It's not equal.
Why are you saying that? I see why you're maybe why.
No.
Scaling, good. It's scaling because all three sides are different lengths, right? Okay, so we know it's scaling. But what we don't know is it a right scaling, is it an acute scaling, or is it an obtuse scaling? Okay? How could anybody have a suggestion how we could determine which one of those three it is? Let me ask you this. If this were a right triangle, which of the three sides would have to be the hypotenuse?
The 5.1.
No. The 8.54, because for a right triangle, the hypotenuse is always the biggest side of the triangle, isn't it? Right? So the question is 8.54, is that the correct hypotenuse for these two sides? Well, the way to find out is let's just calculate what the hypotenuse would be for those two sides, right? I know that 5 squared plus 5.1 squared should equal the hypotenuse squared, right? And so the square root of 5 squared plus 5.1 squared should equal the length of the hypotenuse, right? Because we know, here's the picture we always associate with right triangles, right? You've seen this a million times. If this is a right triangle, and that's A and that's B, and the hypotenuse is C, don't we know that C squared equals A squared plus B squared, right? And so C equals the square root of A squared plus B squared. So let's find out what our C is, what our hypotenuse would be that goes with our legs, or our sides 5 and 5.1. So what is the square root of 5 squared plus 5.10 squared? Does anybody have, do you know what it is? Anybody? Off the top of your head, you can't figure that one out?
Can't talk, sorry.
It is, let's find out, square root of 5 squared plus 5.10 squared equals 7.14, roughly. So I should do this. Okay, so then what does that mean if the third side of our triangle was 8.54? Was it too big or too small to be a hypotenuse? Too big. So does that make this an obtuse triangle or an acute triangle? Makes it obtuse, doesn't it? Now look what. Pretend here that, let's take this right triangle, and let's say that the hypotenuse, which is orange, pretend that that's a rubber band that's been stretched a little bit, right? If I want to make the rubber band stretch so it's bigger than what the hypotenuse should be, doesn't it mean I have to take these other two sticks, A and B, that are hinged right here, don't I have to kind of spread them apart? As I spread those apart further and make the angle bigger, that's going to stretch the rubber band out more, right? Everybody get that? And so because the third side of the triangle was bigger than the hypotenuse would have been, it must have been stretched out a little bit, so it's obtuse. Make sense? Okay, what if, now if we'd had an angle, if we'd had an answer instead, if we'd had the exact answer, 7.14, it would have been a right triangle, wouldn't it? Because it would have fit the hypotenuse perfectly. If it would have been something like 6.35 or something like that, and it's too small, then it would have been an acute scaling. Make sense? So if we go back to our problem, then we ought to be able to pull down, this is an obtuse scaling, and that part at least should be right. How come it's not? Oh, it's filling the rest?
Yeah.
Oh. AB was 5.1, is that right? BC was 5, what was the last one?
8.54.
Hey, how about that? Got it. Okay? Make sense?